Thank you for joining us today. And once again, welcome to Immubit's webinar today, Revolutionizing Process Optimization in Refining, featuring Big West Oil. We've got a very special agenda for you today, which is going to start with a presentation from Travis Legrand, Operations Technical Specialist at Big West Oil, who's going to share a bit about what their company is doing with Immubit's products. And it'll be followed by a conversation from Corey Clark, Product Manager at Immubit, who's actually going to show you the presentation in action and the live software demo. So just a couple of housekeeping items before we get started. This presentation is being recorded, and the recording will be emailed to you afterwards. So if you miss anything or want to share it with your colleagues, you're welcome to do so. If you look in the bottom right-hand side of your Livestorm console, you'll see sections for polls, questions, and chat. We encourage you, if you have questions that you'd like to address to our speakers, to enter those through the questions console. That's what we're going to use to source our Q&A questions for the end of this webinar. If you have logistical questions, like your audio's not working or something else, you can use the chat for that, and one of us facilitators will get back to you promptly. We're going to use polls throughout the presentation just to gauge some questions that we have for where people are in terms of technology and what they're trying to do. And so when we do that, you'll find the polls button in the bottom right, and we'll activate polls at that time. We'll have the live Q&A, like I said, at the end, which will be your opportunity to ask questions of our speakers today, both Travis and Corey. And with that, let's go ahead and get started. The first presentation today is Big West Oil's AI control applications with Immubit. And I'm really excited to introduce to you today Travis Legrand. Travis Legrand is the Operations Technical Specialist at Big West Oil. He brings 13 years of expertise and a demonstrated history of working in the oil and energy industry. As a seasoned process engineer with a chemistry degree from the University of Utah, Travis has a proven track record of optimizing unit economics, ensuring safety, compliance, and successfully managing complex projects to enhance refinery efficiency, safety, and profitability. And at this point, I'm going to hand it over to Travis to take it from here.
Thanks, Allison. A little bit about Big West Oil. We're an oil refinery in North Salt Lake City, a family-owned business, subsidiary of FJ Management. Our crude oil capacity is 36,000 barrels per day. We get most of our oil from local suppliers in Utah and Wyoming, occasionally some from Colorado and Canada. We're also able to process up to 21,000 barrels per day of wax crude oil from eastern Utah. And that wax crude can have some complicated processing issues that we'll deal with. I'll talk a little bit about that as we get into it. We produce gasoline, diesel, LPGs, liquefied petroleum gases, and other refined petroleum products that we sell in the western U.S. states. And our facility employs about 255 people. So some of the challenges that we were looking to solve, the reasons that we were talking with Immubit, I'm going to get into a few of them. So we had changing feed qualities for our MSCC unit, which is a kind of a specialized FCC. If you're not familiar with refining in FCCs, in an oil refinery, you take crude oil and you separate it into gasoline, diesel, LPGs, and then you're left with this heavy gas oil that's too heavy to be diesel. And so we take that and feed it to an FCC unit, and where a catalyst cracks the oil, breaks it up into smaller molecules, turns it into things like gasoline and diesel. The feed qualities have an impact on what products you can make, so we were looking to work around optimizing with those changing feed qualities, and also maximizing overall liquid volume swell. So when you crack that heavy gas oil into the lighter products, it's a lower density, so it actually swells the volume. So if you put 100 barrels of feed in, you'll get somewhere around 112 to 114 barrels of products out. And so maximizing that volume swell obviously is an economic benefit. And we wanted to be able to do that in real time in response to a profit-driven objective function. We also wanted to improve the separation between cat gasoline and olefin in our debutanizer tower. So After coming out of the reactor, we have to separate those products from each other, and two products that we have are gasoline and olefin, which is an LPG that we then, it's an intermediate that we send to another unit to combine with butane and turn it into a high octane gasoline. It's a valuable product, but we make more of it than we can process in that downstream unit. So we want to minimize how much of that we're making and try to push more of it down into the gasoline. We have a tower that separates those from each other, and that tower run in flood and was difficult for operators to control. So we were looking for help in improving that separation in that tower. Some other challenges that we wanted to look at were optimizing the diesel flash in our diesel stripper tower while avoiding flooding the tower. So when you make diesel, you end up getting a little bit of gasoline type material in with it, and you have to remove that material so you don't have too low a flash point. That tower struggles to do that, so we're looking for help there. We also want to optimize our diesel hydrotreating and dewaxing unit. So that diesel, because it comes from a waxy crude oil, can have pretty poor cold flow properties. So you try to put it in a truck and it's not going to flow very well. Might plug up and not work. So we have a reactor that dewaxes it and makes it flow better in vehicles. We also have a reactor that removes sulfur and other poisons from the diesel. So optimizing those two reactors was within its constraints. Another challenge we're looking to work on. Also optimizing the crude unit cut points. So there's a heavy diesel that goes to the dewaxer. There's also lighter diesels that don't have to be dewaxed, but if you can make the cold flow properties better on those lighter diesels, it allows you to get even more diesel out of the FCC. And there's kind of a balance there that you're always trying to figure out what's better, to pull harder out of the crude unit or pull harder on the FCC. So we wanted to really figure out how to optimize that whole diesel pool. There's 3 separate units that have some diesel production. So putting controllers on each of those units and then putting an overarching control over all 3 of those. So once you've got a controller controlling those 3, then you have one that sits above those and looks at what you're producing from all of them. And it may de-optimize the diesel from one unit to improve production in a different unit to overall give you the best diesel production. So our solutions for that, we've so far implemented 3 DLPCs. A DLPC is a deep learning predictive controller. And we've put 3 in, and we're working on a 4th one that's going to be commissioned soon this summer. So these controllers work by looking at many different data points in a unit and kind of taking the snapshot of all those different data points and the ranges that they've all been in over a period of months, if not years, and it can look at all those data points all at once simultaneously and adjust multiple set points in your control scheme simultaneously. It's a difficult thing for a person to do, but these controllers do that pretty well. So our first application was our FCC debutanizer tower. This is the one that I was talking about where we're separating olefin and gasoline. The tower is undersized, so it's constantly running near the flood point. Once a distillation tower reaches a flood point, then you kind of fall off a cliff on separation, and your separation gets a lot worse. So the overhead product is olefin, and the spec that we have to meet for that has to be below 5% C5. So that means molecules have 5 carbons in them. Ideally, you want everything with 4 carbons and less in that stream, but you can have up to 5% of 5 carbon molecules in that stream. The bottom of the tower is cat gasoline, and the spec for that is vapor pressure, which changes seasonally. And so those C5 olefins are they're really kind of gasoline range stuff, but it's because it's the lightest component in the gasoline, the vapor pressure of the gasoline is raised by it. So you're trying to get just the right split there and not pull any of the lighter material, the butanes and that kind of thing down in that would cause the vapor pressure to be off spec. The FCC reactor, you can adjust the conversion in that reactor to make more diesel or more gasoline, more olefins. So a lot of times, especially in the summer, we're really trying to optimize making as much gasoline as possible. But when this downstream tower is constrained by flooding and this products being off spec, we have to limit the conversion on the reactor. So you're kind of leaving money on the table when you do that. So the solution was that we implemented a DLPC, that deep learning predictive controller, and it manipulates the reboiler duty indirectly via flow rate. So that's the heat input going into the bottom of the tower. And it also manipulates the tower temperature at the top of the tower at the reflux return point. And those manipulated variables move continuously and in conjunction with each other. So when an operator is controlling those, an operator will adjust the flow rate on the reboiler or on the reflux, and then see what the tower does, and maybe get some samples and look at it, and then see if they need to make another adjustment. This DLPC is constantly predicting what your properties are and adjusting both the reboiler and the reflux simultaneously, something that a human really just can't do very effectively. So the result of that was we got better separation between the products. We almost immediately saw these results within a day or two of implementing this DLPC. We were able to get more of the C5s, keep them in the cat gasoline. And as a result, that allowed us to reduce our contract sales of excess olefin. So like I said, we made more olefin than we're able to produce in our downstream unit. So we sell the excess, and it has some value, but it'd be much more valuable if we can keep it in our gasoline, and we've been able to do that. We've also been able to increase our reactor conversion by being able to process this tower without hitting the flood point, process more gasoline to this tower without hitting the flood point. And reducing that vapor pressure of the gasoline has also allowed us to increase our butane blending in our overall gas pool, which has provided value as well. So you can see in these charts on the right that there are different gasoline vapor seasons. So those numbers on the bottom are the RVPs. And you can see the amount of volume improvement that we've gotten during those different seasons. So if you see the 10 and the 11.5 season, it looks like from the DLPC actually lost some ground and it lost some volume there, until you look at the bigger picture and realize that we had a little bit less gasoline production coming from this unit, but overall it allowed us to get a lot more butane in during that higher vapor pressure season. Second application is our reactor. So this is what's upstream of that tower. And our challenge here is that the riser temperature was held relatively static, resulting in money being left on the table. So operators would maybe change that temperature once a week, roughly, just to try and maximize the conversion and the products that you're getting, that you're cracking from the gas oil. So in this solution, we built a DLPC that adjusts that reactor riser temperature continuously. It's constantly making small moves on it to adjust to maximize conversion. We also have some equipment constraints downstream, so it's looking at those constraints and kind of pushing right up against them so that you're just getting the most out of it that you can. And that it optimizes to an objective function. So every product coming out has a dollar value assigned to it that we update, roughly monthly, the dollar values of that. And if those dollar values change, it changes what products it's making to get the most bang for your buck from this reactor. So the results were good initial yield improvement. We did see, we changed our crude tower recently. We had a turnaround this spring, and that really changed the feed qualities of the feed coming to this reactor. So we initially saw really good improvements, and then we've had to kind of go back and retrain the model. We're working on retraining it right now based on the new feed that we're feeding to it. But you can see in this chart here, the baseline to the left there, our liquid volume yield was roughly 113.7%. So for every 100 barrels you're feeding, you're getting 113.7 barrels out. And after implementing this DLPC, we pushed up above 114%, as high in January as 114.6%. So, and you can see that the little diamonds there are the temperature on the reactor, and it's moved around a lot more than we typically would using this DLPC, and that's allowed us to get that additional volume swell. The third application was our diesel stripper tower. So due to tower flooding, we had to run with the diesel flash point much higher than the desired to stay on spec. So we didn't want that to dip too low. You've got a flash spec that you have to meet to be able to sell your diesel as a product. And just to make sure that we weren't ever going below it, we had a buffer there of about 5 degrees. And so as a result of that, we're also making more naphtha than we wanted to. So that's a portion of material. You know, there's a portion of material between gasoline and diesel that really could be either gasoline or diesel. And in general, we want to keep as much of that in diesel as possible, but still meet that flash spec. And the flash point lab sampling is less precise than other samples are, just because of the testing methods. And because it's less precise, that also kind of pushed us to keep that 5-degree buffer in the flash spec. Our solution there was a DLPC on the tower that manipulates the reboiler rate and reflux rate simultaneously, much like the previous tower that I talked about. It's moving both of those continuously and predicting what the properties are in real time, so that you can push up right against those spec limits without exceeding them. The result of that, this is a newly implemented DLPC. It's been online for a few weeks now, but we're already seeing some results, improved results from it. We were able to build a reliably accurate inferential for diesel flash. So the inferential is basically, it's looking at all the different data points on the tower, and it's predicting what your flash properties are without having to run a lab sample on it. So you may run a lab sample 4 or 5 times a day, and you adjust and then see what you get a few hours later. The inferential is continuously telling you what your properties are, and it does a pretty good job of that, so that we can continue to adjust operation without having to wait for lab samples. And so far we've been able to reduce that buffer on the flash from 5 degrees down to 3 degrees and still keep our diesel on spec. So in summary, these DLPCs have been successful for us, largely because of strong participation from engineering, operations, and economics groups during development. So this gave the Inuit team a solid understanding of the opportunities that we were looking to improve and the constraints that we had to work within. We need to know where our constraints are to be able to help us push up against them and make the most improvements. And early operator buy-in really was key to our success. If operators don't trust the technology, they're going to be reluctant to keep it engaged. You know, the Inuit controller, they can turn it on and off, and if they're not comfortable with what it's doing, they're going to turn it off. But getting early buy-in from them has really helped to keep our engagement up. We had senior operators involved with the development right from the beginning, so they were familiar with the technology and its capabilities. They were comfortable with it. They passed the word to other operators. And then before implementation, we trained all the operators. We wanted them to be familiar with what it looked like and what it's going to be doing. And all that went a long way to help get buy-in from operators early on. As a result of that, you can see, we measure the success of operating the DLPCs by engagement. So this is the engagement of the 3 different models that we're currently running. And above 85% engagement is considered successful. So the lighter blue one is the debutanizer model. That's the first one that we put on last summer. And you can see immediately we had above 95% engagement as soon as we put it on. Operators were really confident with it. In October, that's a spec change month where it wasn't always doing exactly what we wanted it to do. So we had a little bit of tweaking from Inuit's continuous improvement team to get that back to operating as well as we wanted it to. And then after that, you can see engagement was even better, almost 100% engagement, going through the winter. In February, it dropped off fairly low. That's because that was during our turnaround when the crude unit was down, and our feed to the FCC was really different from what it normally is. So we didn't have it engaged as much because it just didn't know how to operate with that feed. It needs to be retrained for that kind of a feed. But coming out of the turnaround, we've had pretty good engagement again. The reactor model as well had really good engagement, and the HTS stripper, as you can see, for the month that it's been on so far has been pretty good, right about 85% engagement. Now I'm going to hand this off to Corey with Immubit, who is going to explain how all this works.
Thanks, Travis. So my name's Corey. I've been with Immubit for almost 5 years now. Before I joined Immubit, I worked as a process engineer at a refinery in North America. And when I started with Immubit, I worked as an implementation engineer. So these are the engineers who design, develop, and deploy the closed-loop neural network optimization strategies that Travis just talked about. So I worked for a variety of our clients throughout the US. For the last 2 years, I've been working as a product manager for Immubit. So I work really closely with our software team to develop some of the products that I'm going to demo for you today. And these products essentially are set up to allow customers like yourselves to develop, maintain, and monitor their own neural network solutions. So before I dive into the demo, we're just going to take a second here, maybe a couple of minutes, to do a poll. And so you should see in the bottom right-hand side of your screen, there's a little red circle with the number 1 in it right above the poll symbol. You all can go ahead and click on that. There's a poll there. Let me just do it too. And it's going to ask you where you're at with your AI journey so far. So if everyone wants to just go ahead and take a couple of seconds to answer that poll. Okay, so I can see, yeah, we're pretty split across the board here. It seems like the majority of people are just at the start of their AI journey. So that's very exciting. I'm glad to have you here. We hope you are as excited about AI as we are. And we have I guess it goes down. Most people are just at the start of their journey, and then we have some people who are already using AI and loving it. So that's great too. So real mixture here of responses. I'll give everyone a couple of seconds more just to answer, and then we can kind of move on. Okay. So before I dive into the demo, I want to just take a step back and give a very high level overview of what Immubit actually does with its core technology. So our core technology, as Travis just kind of explained, is the development and deployment of closed loop neural network solutions to control and optimize your underlying process unit. And the way we do this, and the way we actually develop those controllers and optimizers, is we actually train several layers of neural networks throughout our kind of project lifecycle. So our first layer is our inferential layer, which Travis talked about too. Inferentials are not unique to Immubit. They're not an Immubit technology. Other technologies use inferentials too, but essentially what inferentials do is they infer what the real-time value of a property is, where that property is otherwise slow sampled. So for example, if you have a diesel flash point that you really care about and you want to control and optimize to diesel flash, you probably only sample diesel flash 4 times a day. So you don't really want a controller and an optimizer that can only do its job 4 times a day. So what you can actually do is you can develop a mathematical model that will infer what the property of that diesel flash is in real time. And it does that by using fast sample variables in the unit. So any flows, temperatures, pressures that make sense in developing this model to kind of infer what that flash is. So that's our first layer. It's our inferential layer. Not all projects will have inferentials, so this is an optional layer, but we typically find that most projects do need some sort of inferential property. Our second layer is our DLP layer. This is not an optional layer, and this is a very critical layer for us. And our DLP, what it is actually a dynamic process model. And so what this layer does is it takes all of the key independent and dependent variables from your process unit, and it trains over hundreds of thousands of episodes, where an episode is like the time to steady state of your process unit, so usually 2 to 3 hours. So it trains over hundreds of thousands of those 2 to 3 hour episodes, and it uses the value of the independent variables over that time frame to then predict what the dependent variables will do in the next 2 to 3 hours. And what this really allows us to do is then to build an offline simulator of your process unit, where we learn the true process relationships and dynamics. This is a neural network, and one of the benefits of using a neural network in this way is that when we learn the relationships between the independent and dependent variables, we don't have to make any assumptions, we don't have to make any simplifications or linearizations of those relationships. And we can also learn the true time dynamics of those relationships too. So we end up with an offline dynamic process model that is truly representative of what is going on site. That's critical because our third layer, which is our DLC layer, so this is our controller and optimizer, that uses the DLP during its training process. And what the DLC does, how it works, is it uses a technique called reinforcement learning to essentially teach itself how best to control and optimize your unit. So as the user, what you do, you define what good looks like for your particular process unit. That's typically a combination of maybe an economic objective function that you want to maximize, combined with your unit constraints. So you might have an overhead temperature you don't want to exceed, or some inlet pressure you don't want to exceed. And then maybe you have some other targets too. Maybe you want to hit a certain octane target, or maybe you want to stay above or below a certain diesel property. So all of those things combined are typically what good looks like for your unit. And so again, as the user, you define what good looks like. You tell the algorithm, hey, this is what good looks like. And then the DLC, over hundreds of millions of different episodes, again, that's those 2 to 3 hour spans of time, over hundreds of millions of those episodes, it essentially moves whatever handles you tell it can move, feed, reactor temperature, and it measures the outcome using the DLP of those moves, and then it can see how good was that move that I did. Again, it does this over hundreds of millions of episodes. So what happens is that you end up with this algorithm at the end that's kind of learned over these variety of process conditions what the best move is to make at any time in order to meet that good, whatever you define good to be. The way I like to think of it is, imagine you take your best operator who remembers everything, and the way you train them is you say, hey, you can sit on the unit and you can make any move you want to make with the handles we give you. You can wait and measure the response and see how the unit behaves. You can do good things, you can do bad things, you can just do whatever you want and learn really how the unit works and how to optimize it. And we're going to let you do that for 24 hours a day for hundreds of years, and you're going to remember every single thing. That's kind of an analogy to how the reinforcement learning algorithm works, and it's how I like to think about it when I explain it to others. So again, this is a very high-level overview of our core technology when it comes to our closed-loop neural networks. But some of the other ways that I'm going to show you that our technology can create value outside of that closed-loop neural network is using our IMUBIT platform. So Travis talked a little bit about some of the problems that Big West Oil was able to solve with IMUBIT. And one of the problems we were able to solve was the kind of multi-unit or the hierarchical model optimization. And we all know that to truly optimize a process unit or a plant, you don't just want to optimize individual process units on their own little island. You really need to start to optimize across units. This is true optimization, but it's also very challenging. One of the challenges that can kind of arise from that is that typically on site, what you'll find is that within each process unit, you kind of develop these own little mini silos. So maybe you have a crude unit and an FCC, and within each kind of process unit, you probably have 2 different process controls engineers, 2 different process engineers, definitely you have different operators, you may even have different economics folks. And so people are kind of pretty good at optimizing within their little silos, but when you're trying to optimize across process units, it can become challenging. Particularly if one unit, so in this example I'm going to show you, if the crude unit is actually constraining the FCC. And so for the FCC folks to be able to identify that they're being constrained by the crude unit and then communicate that in an effective way to the crude silo so that they can start to debottleneck the FCC, again, that's really challenging, but it's something you can use our technology to help with. And so every model that gets deployed on site will get a dashboard in our DLPC performance dashboard here. So for today's demo, you can see here, I have 2 units. I have an FCC unit and a power former. Today, I'm interested in the FCC. For this example, let's pretend I'm the FCC engineer. So I'm going to come in here to my unit and I want to understand what is constraining the FCC? What am I being constrained by? So to do that, I can navigate here to the constraint widget, and I can very easily see that this yellow bar here on this MV, which is the vac tower resid feed to the FCC, is the main constraint. So for 92% of the time over the last 7 days, I've been constrained by this upper bound, which has been around 4,400 barrels per hour. That's where it's been set. Now that upper bound isn't being set by me, it's being set by the folks on the crude unit. So let's now look at the last 30 days. And we can see that, hey, in the last 30 days, this MV was actually allowed to run over 6,000 barrels per hour. So as the FCC engineer, I don't need to know anything about the crude unit. I don't need to talk to the crude operators, but I can see that something's changed in the last 7 days, that I'm now being more constrained on my unit than I was in the last 30 days. So I can use our collaboration feature here, which is our note feature. I can come in here, I can save a snapshot of this page via URL. It'll have all of the things that I'm zoomed in on saved. I can leave a note explaining that it looks like we're being constrained by the crude tower. And now I can add this note, and then the really cool thing I can do is I can copy the link to this note, share it with my colleague on the crude unit, who can click on this link like they've done here, and they're going to open up the exact same page with that 30-day time range that I set. So now they can come in here and they can quickly and easily see, hey, yeah, we are constraining the FCC with this VAC tower resid upper bound. I can see that in the last 30 days it was set more leniently. I can see that it's now being clamped in the last 7 days. Maybe now I can truly understand that I'm constraining the FCC, and I can go and talk to my operators and see if there's anything we can do about relieving this constraint. And all of this can be done via our notes feature, which again is one of our main collaboration features in the platform. The second example that Travis talked about a little bit was inferentials. So inferentials, as we already talked about, are kind of key variables in a lot of projects. The example Travis gave was the diesel flash inferential. And what happens when inferentials are deployed on site is it becomes really critical that they continue to do a good job of inferring what that property is on the on-site data that they're running in live. And so inferential performance is really a kind of a key KPI for most projects that use inferentials. And one of the ways that we can use the MUBIT platform to collaborate between different personas on site and try and solve that problem of keeping your inferentials up to date is, again, using a combination of the performance dashboard. So let's say today we're interested in the LCO 95% point inferential. So someone maybe at the project management level can come in here and they can look and see, hey, my error for this inferential over the last 7 days was around 8.9, but my error over the last 30 days was 6.81. That seems to me like the error on my inferential is trending up. That gets me concerned. Let me again add a note here, which will keep all of this information. I've zoomed in on 30 days. It will keep all of the information that you see in the dashboard as part of the note. So I can now leave this note saying, hey, inferential performance looks like it's not doing so good. I can then share that with the person on site who's responsible for this inferential. Maybe it's the process controls engineer, maybe it's the process engineer. Again, I can save the note and then I can share the note directly with them. They can take a look. And then what that person can actually do is they can use some of our other features in the platform to really dig in to see what's going on with the inferential. So they'll come to our model evaluator here. Again, they'll pull up the LCO 95% point inferential. They'll look at the appropriate model, and they can use this feature called unseen data. And what unseen data is, it's data that's streamed live from site to the MUBIT cloud, and what it allows you to do is monitor all of the models that are deployed on site, inferentials or controllers, and see how the performance is doing on live on-site data. So I'm going to zoom in here. I'm going to see my unseen data. And what you can actually also see over here on the right-hand side is all the metrics for the unseen data. So that's data that the inferential has seen while it's been on-site versus the data that it was tested and trained on. And so I can see my accuracy here, my error metrics, and what I can actually tell is that, hey, it looks like since the inferential has been deployed on site, actually it looks like the mean error of the on-site inferential is kind of better than it was when it was in testing. And so, yeah, as a process engineer, as a process controls engineer, I'm probably going to spend a little bit more time evaluating this inferential. But for the sake of this demo, we're just going to click through some metrics. But all of these metrics that I'm seeing are showing me that the inferential performance is doing pretty much as well on site as it was when we trained it. So I've given myself confidence that I don't think the inferential performance is degrading. And what I can do now is I don't just have to tell Travis or tell the project manager that it looks good. I can actually save this analysis. And again, everything that you see here, so we're zoomed into the specific time period, all of that information is saved with the note. So when someone reloads the note, they see it the exact same screen. So I can do my analysis. I can add a note here. I can save all my thoughts, my conclusions from my analysis. And then Travis doesn't just have to take my word for it that the inferential looks okay. Again, I can copy this note URL and I can share it with him. He has access to this too, so he can easily come in here too, see my analysis, and really understand that, hey, get himself comfortable with the fact that, yeah, the inferential does look like it's doing okay. And so again, this is the real power of the MUBIT platform. outside of the closed loop neural network controllers and optimizers that are deployed on site, you can use the Immubit platform for collaboration features and to really democratize the data so everyone's seeing the same thing. All the different personas on site have access to the same features, the same functionality, all the different silos, whether you're the crude engineer or the FCC engineer, you can come in and you can kind of see how each other's units are doing. And it really helps just get everyone on the same page, talking the same language. So when you're trying to solve some of these really tough problems, like cross-plant optimization and control, which is a very difficult problem to solve, you can use the Immubit platform as a really key tool in trying to help when it comes to the collaboration that's required in order to do that. So I think we'll pass back to Alison now.
Awesome. Thank you so much for the explanation and the demos, Corey. And if any of you on the call saw the product and want to interact with it, we encourage you to sign up for one of our interactive engineer versus AI duels, where you can pit your best optimization team against Immubit's AI and see if they can better optimize a unit than the AI duel. So with that, we're going to open the floor for audience Q&A. We've had a ton of great questions come in through the questions console during the course of the call. Some of them, it's clear, are directed at Travis, some are directed at Corey, and I'm going to kind of facilitate to the two of them. So I'm going to ask Travis and Corey to join me once again, and we'll go ahead and get started. So my first question, Travis, is for you. It's actually two sub-questions. Were your operators already using advanced process controls before DLPC? And whether yes or no, how difficult was it to sell the AI-based control to operations?
We did not have any advanced controls before, no APC. When we started talking to the operators about using AI to control, there was definitely a healthy amount of skepticism from them. They were skeptical that it would work. Some were skeptical that it'd be kind of pushing them out of a job. So getting them familiar with it early on was definitely helpful in getting buy-in from them. And also, I think starting with a simpler model really helped. So we started with that debutanizer tower. It's not as complex to understand as a reactor model. It's just controlling reboiler and reflux, something that the operators are very familiar with. It was doing it continuously, so that's something that they weren't used to. But they saw immediate results from it, and within a week, I think all of them were totally on board with it. Like, this is great. Let's put it other places. So,
awesome. Yeah. Thanks, Travis. Next question, I'm going to actually ask to Corey first, and then I'm going to ask Travis to comment on your specific scenario. So for Corey, can you comment on the architecture of Immubit's DLPC? Is the runtime control running on the process control network?
Yeah, so we can, when we go on site, we can actually connect to the DCS, or if you have existing APC solutions, we can connect to your APC. So yeah, we sit at the DCS level, and we write set points out to the DCS. Again, if you have APC, we can also write set points out to any existing controller that you have. So yeah, we sit on the PCN level.
Yeah, that's how ours works. It sits in the kind of the demilitarized zone and
yep.
receives feedback from Immubit and then writes set points to our controllers.
Yeah, I will add, when we pull your historic data, though, we typically pull them from your on-site historians, which typically is at the business network level. So our data extraction, we connect to the business network level. But yeah, as Travis says, we like to sit in the DMZ zone and then funnel through to your DCS or your APC like that.
Next question we've got is for Travis. How varied is your crude slate and the subsequent FCC feed composition? Does the model need to take that into account for the DLPC?
Yeah, it does need to take that into account. So our crude slate is actually pretty stable, especially compared to other refineries. We've got 3 or 4 base crudes that are really the majority of what we run most of the time. We change the percentages of those a little bit, but it's pretty stable. The wax crudes are really what makes an impact on the FCC. So we have to run a minimum of, historically, we have to run a minimum of 30% black wax to make sure that there's enough coke make to, for the heat balance in the FCC, and also a maximum of 70% so that we're not running too hot and off control on the heat balance. Those percentages we've been challenging more recently as the wax crew drillers have been getting into horizontal drilling. They're producing a lot more yellow wax and less black wax, so trying to keep that minimum 30% black wax has been difficult for us. But we've also seen changing properties in the black and yellow wax where they don't quite act the way they used to. So that's been a little bit challenging to try to optimize around for us. But we had enough operating data in that newer regime that the Immubit controller was able to take all that data and adapt to that very well. We did make a pretty significant change to the feed when we put our new crude tower in, and we're basically pulling more diesel out in the crude tower, putting less diesel in with the FCC feed. And so because of that, we're working on doing a retrain of the model, which we should be implementing fairly soon. It's a little bit involved to do a retrain, but it can be done. I think they prefer not to do it more than like once a year, but even needing that retrain because properties are a little bit different, it's still directionally moving the ways that we want it to move. We still have pretty good engagement with the DLPC, even though our feed property has changed a bit.
Travis, that response is perfect. It led me into a little follow-up question. So you mentioned how often you guys are retraining the models. What plant personnel are involved or required for these retrains?
Really doesn't need much input from the plant. Immubit is collecting the data continuously. We're streaming them the data all the time. So when the model is running, it's not actively learning from new operating conditions. It's been trained on a select set of data, and that's all it knows. So Immubit's still collecting the data, and they'll ask us questions about what changes have happened and what we're seeing, and so we'll have meetings with them periodically to kind of talk through those kind of things. But they're really doing all the work to collect that data and do the retrain.
So our next question is around advantages of using Immubit's DLPC versus any traditional APC application package. Corey, I'm going to ask you to address it in the general capabilities, functionality sense. And then Travis, I'd love to get your opinion because when you guys implemented Immubit, I'm sure you did a little bit of research on what else is out there. Can you explain a little bit more about why you guys chose to go with DLPC in a situation where you didn't already have APC? So Corey, lead us off.
So one of the, there's many differences between us and traditional APC technologies. I'll cover some of the higher ones. The way we train our DLP layer, which is our process simulator layer, we train it using a neural network. And what that allows us to do is we learn the true process relationships and dynamics. So we don't have to make any linearizations or approximations. And so when you have a unit like a hydrocracker or an FCC, where reactor temperature doesn't really have a linear relationship to your products. So a hydrocracker is probably the most obvious one. At some point as you increase reactor temperature, you're going to produce diesel. At some point, you're definitely going to hit overcracking. And then the increase of reactor temperature will cause a decrease in diesel. That exact temperature that the overcracking occurs varies, obviously, depending on your feed slate at the time, other process conditions. And so when you really start to think like, how can I linearize these relationships? It becomes very, very difficult. And when you start to linearize relationships like some of typical APC models do, you can actually end up losing a lot of value because you're having to oversimplify things. So you might come up with an answer that says always increase reactor temperature, when in reality, that's not what you want to do. And so again, because we use a DLP layer, which is a neural network layer, we don't have to make any assumptions. We don't have to bake in any first principles. We learn the true process dynamics and the true process relationships. And so that really allows us to be able to optimize to your actual process unit. The other big difference with us is our DLC layer, our controller and optimizer layer. So we're not an online solver, and we don't actually solve anything online. We don't do any calculations online. Everything's done offline. when it's trained in the cloud. And the use of reinforcement learning for this is really unique to Immubit. I think, as far as we know, to the best of our knowledge, we're the only company in the world that does reinforcement learning in closed loop. And reinforcement learning is such a strong and like really powerful technology, because it trains, like I explained earlier, over those hundreds of millions of different episodes. It can tweak prices, it can tweak constraints, it can change all of those things. And so it really learns very similar to how a human brain learns. And so using that kind of powerful technology to be able to actually learn to control and optimize your plant is very, very, very unique to us. It makes us different from other technology, and it really is what sets us apart. I don't want to take too much time with this answer, but it's kind of what the analogy we always use. Like, if you're learning to walk as a child, you learn to walk by trial and error. You fall all the time. Those of us who have kids have watched that with much joy. But that's how a human brain learns to walk. You just kind of trial and error it, which is similar to reinforcement learning. The kind of APC analogy of walking would be, every step you took, you would have to get out your protractor and your ruler and your calculator, and you'd have to measure the gravitational force, and you'd have to kind of solve it online to see how high should I lift my leg to take a step. So it's kind of analogy to, what would be the better method to learn to walk, the sort of method that humans use, or, this kind of heavy calculation sort of online solver method. So those are some of the really big things that set us apart from existing kind of technologies out there.
Thanks, Corey. Travis, anything to add?
Yeah, so for us, we'd evaluated APC several times and looked into what it would take to do. And being a small refiner, it would have taken a lot of resources on our side to implement something like that, and we probably didn't really have the instrumentation everywhere that we needed it to successfully implement it. So when we started learning about Immubit, this technology really seemed to us like it was kind of the next step above APC, but we could jump right over APC and not have to go to that. We'd skip straight over it and go to something that would work even if we were limited on instrumentation in some places, and also where the Immubit team does a lot of the heavy lifting when building it, and it doesn't require really a whole lot on our side. So those were definitely advantages that we saw in using this technology.
Thanks, Travis. And I'm going to direct my next question to you as well. How long would it take to train the DLPC model, like in the example you mentioned where the crude unit was updated over the turnaround?
Yeah, so you need to have a good amount of data, ideally at least a few months. So we've had our tower up and running since March, and we've decided to just start doing the retrain in the last week or so. And I believe they'll plan on having it implemented within the next couple of weeks. So I think it really only takes a few weeks for them. We have a few projects they're working on, but we asked them for them to kind of shift focus to this temporarily. But you definitely have to have some time pass so that it has enough data points to be able to make good inferentials and good determinations of what will happen when you make moves.
Awesome. It's like a baking recipe. Total time, very long. Active time, very short. There's just that data collection period. Corey, I've got a question for you on what happens if you lose a manipulated or a controlled variable in the controller, for example, because the instrument isn't working right or an analyzer goes out or something like that.
Yeah, this is a great question. So if it's unplanned, the model will turn itself off. So if we lose a critical piece of information and we didn't plan for it, the short answer is the model will turn itself off. Now, there are steps we can take in order to mitigate that. So if you have a manipulated variable that hey, half the time we don't run feed through this line. So this is only really a manipulated variable we can use for 50% of the time or 70% of the time. If we know that during the planning process, we can actually make that manipulated variable what we call a flexible MV. And so when it goes out, the model then knows, hey, I can no longer use this MV. I'm going to use my other handles to compensate. And so you can actually continue to control and optimize through that. With controlled variables, again, we have flexible constraints. So if you have a control variable that we know ahead of time, you only really need to control to some of the time, we can kind of build that into the model as well to give you sort of flexibility to be able to run through kind of these expected process upsets, sorry. We also have some other features that you can use. We have a bad value protection. So let's say you have an instrument and you know it might go out, maybe it's a temperature indicator or something, but you as the site feel comfortable like, hey, when this temperature indicator goes out, I either want to switch to another TI, or I can just use a default value of 500 degrees Fahrenheit because it's going to be a short period of time and it's not critical. We can kind of build those things into the models too, to give you, again, kind of flexibility to run through these upsets. So again, if it's planned or if we know about it ahead of time, we have a lot of flexibility of how to keep the model on site. But if it's unplanned, you just lose something in the field because a pump goes out, then yeah, our models will turn themselves off.
And then Corey, I think this next question may be for you as well. So does the Immubit DLPC have automated feedback, like lab results or analyzer results to help adjust inferentials without human intervention so that the model stays up to date with slow changes to unit operation?
Yeah, absolutely. So we bias our inferentials on site. There's a couple of different ways we can do it. We can use like a cum-sum method, or we can use just kind of a straight sort of linear biasing method. Again, this is something that our implementation engineers will talk to the folks on site about when we're setting it up to just hone in on those coefficients. Very similar to how other technologies bias their inferentials too, based on the most recent kind of lab samples. So yeah, that's absolutely something we do for inferentials. We do on-site biasing.
Next question is around how the DLPC is integrated with economic information. So how does it get the economic or cost data in order to do the optimization? And I'm going to ask both Corey and Travis this question. Corey more generally, but then Travis interested in what the architecture setup at Big West Oil looks like to get that information.
Okay, so
Corey, we'll start with you.
Okay, so again, we have a lot of flexibility here. So the way I've seen it done before is several different ways. Some people will push their prices from their LP either to their Pi network, so to their historian network, or straight to their DCS. And then we can read those in real time when there's changes to the model. So let's say it's Monday morning, you've updated your LP, you've got new prices now for everything. You can push those to Pi or to your historian. That can then get pushed to your DCS. And then we can feed them in real time to the model. Alternatively, if it's something that people want to have a little bit more control over, we can have it set up. So in our on-prem DLPC application, you can come in and manually enter the price changes. So there's, again, a bunch of different ways we can do it. But the key point is that we do, and it's a really critical point, in order for our models to control and optimize, we do need to have the most up-to-date prices. And so the more often you change prices to reflect the current market conditions, the better the model's going to do for you. So feeding in those prices in real time is absolutely a critical point to our optimization.
Yeah, so our prices come from our LP, but we didn't want it to be an automated thing. We wanted to have control over when those prices hit the model, because it's going to change how the unit operates. So the operators need to know why changes are happening in their unit. So the way we handle that is our economics engineers will contact operations and myself or our operations manager and say, we've got a new price deck that we want to push through, and we use Pi, so they have a spreadsheet basically where they'll put the new price deck in, and from that spreadsheet it pushes it to Pi, and once it's in Pi, then it automatically updates in the DLPC. Our internal policy on that is they contact operations supervision first to make sure that it's okay to make a change. The unit's in a stable condition where changing the operation of it isn't going to be detrimental to them. And once we give them the go ahead, then they'll call the operators on, hey, I'm changing your price index. You might see it trying to make more LCO.
Awesome. Thanks, Travis. So one final question for today, and I'm going to direct it at Corey. And the question is, has Immubit worked with other petroleum refineries for similar types of optimization?
For similar types of optimization that Travis showed today, I'm going to assume that's the question. Yes.
Sure.
Yes, I think we have at last count 90 different models that are running in closed loop in North America. Some of them very similar to what we did at Big West Oil, some of them different. But yeah, we do have that idea of that hierarchical model is something that's newer for us. Like we, maybe in the last couple of years really started developing these hierarchical models. But yeah, we do have other cases where we've done similar things at North America refineries.
Thanks, Corey. And yeah, I think we always say we're working with 7 of the top 10 biggest US refiners. So you're in good company if you're using Immubit's DLPC application. So we had a ton of questions come in through the questions console today. We don't have time to answer all of them online. All the questions that we didn't get to today, you'll receive a follow-up email from your Immubit account exec who will either share the answers to the questions or set up some time for you to talk to some of Immubit's experts to get a detailed answer to your question. I just want to thank our presenters one more time, Corey and Travis. You did an excellent presentation today. It was great to hear what Big West is doing and also to see kind of what's going on behind the scenes of what makes Big West's success stories and results possible. So thank you guys, and thank you to everyone who joined us today. We hope you have a fantastic rest of your day or evening, and we'll send those follow-ups out as well as the link to the recording after this.